Hello, my name is Michael Matejka and I'm taking Everyday Physics 1550 at Lakeland Community College for the fall semester. I'm pretty bored. What should I do today? I know. I'll make a Cartesian diver. Now I gotta find some supplies. Oh look, there's a random Coca-Cola empty bottle I can use. Now only if there was a pipette I could use. Oh wow, one just appeared right in front of me. Let's get to work. First, I'm going to start off by filling up the empty Coca-Cola 2-liter. Filled water to the top of the 2-liter to make sure that the pipette is fully immersed in the water. Now I'm going to fill up the pipette 3/4 of the way so it's easy to squeeze the bottle to go forward with the experiment. The next step is to put the pipette into the bottle and screw on the top. This is what the final product should look like all together. The pipette is in there on the top, filled 3/4 of the way. I took off the label so it is easier to see what's going on with the Cartesian diver. The word Cartesian is from a French mathematician by the name of Rene Descartes, even though the first person to write about the Cartesian diver was Raffaello Maggiotti, which in fact was a student of Galileo. Obviously the dropper is the diver, but watch what happens when I squeeze the bottle. The dropper sinks. If I let go, it comes up. Now I'm going to talk about Archimedes' principle. Archimedes' principle is an important law in physics. Archimedes' principle is based on buoyancy. The principle states that an object that is in a fluid will be buoyed by the force equal to the weight that it displaces. In this experiment, the fluid is regular tap water. The Cartesian diver is an experiment to help show the relationship between buoyancy, volume, pressure, and temperature. In this experiment, the temperature is constant, meaning we are focusing on the pressure and volume, but I'll explain more of that when I talk about Boyle's law. Now, I'll be explaining why the dropper sinks and why it floats. When I squeeze the bottle, the dropper air volume decreases. This is happening because more water is going through the dropper, increasing the water volume inside the dropper. This makes the dropper sink due to the lack of air in the dropper. The reasoning behind this is because air is less dense than water. When there is more water compared to the air in the dropper, it sinks. When I let pressure off of the bottle, the dropper proceeds to rise, and this is a reverse process of how the diver went down. When the pressure is let up, the dropper rises and water is released from the dropper, increasing the air in the dropper. Now, let me show you what I'm talking about when I say that the dropper sinks when water goes inside of it. So, the water level is right there. When I squeeze and give pressure onto the bottle, water will go inside of the dropper, causing it to sink. Watch. See? It just went up. Now if I let go, the water comes back down. Squeeze, let go. Just to inform you about the temperature relationship, if the temperature is decreased, the pressure remains constant. A result to this would essentially decrease the volume of the air in the dropper, allowing it to sink to the bottom due to the decrease in buoyancy. If the temperature is increased, the dropper floats from the dropper, releasing the water and increasing the volume of air inside the dropper. Now, you may be wondering, how does all of this tie in with a real-world scenario? Well, fish have a sac containing air inside of them. They can control the buoyancy they have by releasing or taking in air. This is pretty interesting because it shows us how fish can go to different depths of water. Here's an explanation on gravity with the experiment of the Cartesian diver. Along with buoyancy, there's gravity. The gravitational force toward the Earth works against buoyancy, which pulls an object upward. The water immerses the diver, so it creates buoyancy. In order for gravity to win the force of sinking an object, the object must be more dense than water, causing it to sink. With that being said, air is less dense than water. So when water goes into the dropper, it allows it to sink. But when I let go, air goes back inside the dropper, and air, once again, is less dense than water, so it goes up to float. With all that being said, if I release all of the water out of the dropper and put it back inside, it makes it much harder for it to sink, but it still is possible. The reasoning behind this is because it is submerged in water, so if you apply pressure, water will inevitably go inside of the dropper. But let's see what happens if there's water fully inside the dropper with no air. I was able to get almost all of water inside the pipette. Now just watch how slow it goes up when I put it in. It almost went down all the way because if there was all water inside of it, it would sink all the way to the bottom. But due to the little air inside of it, it went back up to the float. Now that I've gone over Archimedes' principle and how it works with the Cartesian diver, now I can explain how this experiment deals with Boyle's law. Boyle's law was published in 1662, and it states that the absolute pressure and volume of a given mass of confined gas are inversely proportional if the temperature remains constant. The equation for Boyle's law is the initial pressure times the initial volume equals the final pressure times the final volume. The easiest way to show you how Boyle's law deals with this experiment is to compare it to the pipette. Like I said before, Boyle's law has the pressure and the volume inversed. I'll show you what I mean. If I squeeze the bottle, the pressure inside increases and allows the pipette to sink. This also decreases the air inside of the pipette, which means that the volume decreases. So as the pressure increases, the volume decreases. Now if I let go of the pressure decreases, but the volume increases of air inside of the pipette. To demonstrate this mathematically, let's assume that the dropper sits in the middle of the bottle like a submarine. Remember, temperature is constant. Let's say we know the initial pressure, the final pressure, and the initial volume, but we don't know the final volume. In order to find the final volume of air in the dropper, we have to divide both sides of the equation by the final pressure in order to isolate the final volume. So, what we do is this. We divide both sides by the final pressure, and that gives us a final equation of the final volume equals initial pressure times initial volume divided by the final pressure. Once you figure out the equation, you can plug in your numbers to find the missing value. This can be used to find everything in the equation as long as you know 3 of the 4 variables in the equation. Thank you for watching my demonstration on the Cartesian diver and how the Archimedes law and Boyle's law relate to it.